Very, very happy to have Ryan Williams today to talk about this fantastic new result. Ryan has been famous for doing a lot of interesting and groundbreaking work in complexity. I mean, maybe one of the most famous ones until now was proving that ACC cannot compute next. And I think people thought that that's the case, but this result, I don't know anyone who thought that this is a true result, so.
Certainly not me.
Certainly not there, Ryan, so I'm looking forward to hearing it.
Thanks for the introduction. Right, so the goal of this talk is to understand the question, how space efficient can time-bounded computation be? So suppose we have an algorithm A that uses t time. Okay, so we want to find an algorithm B. So we find a B that's equivalent to A, does the same thing, say has the same outputs, and it uses minimal space. So the minimal amount of memory possible. Okay, so canonical problem in this sort of line of thinking is the circuit evaluation problem. So circuit evaluation, also called the circuit value problem. I'm given an input, Boolean input, x1 through xn. I'm given some Boolean circuit, C, with ands and ors, let's say maybe some XORs in there. Okay, so I'm given this input, I'm given this circuit, right? And I just want to compute the output, the single output. Right now, if this circuit has size S, so it's got S gates in it, okay, then it takes about S time on most computation models, the ones that we care about, to solve this circuit value problem. Okay, and you might think that, you know, if I'm looking at trying to evaluate the circuit, it could take omega S space. It could take it at least S space, because it's very easy to cook up circuits where there are lots of cuts, you know, of wires crossing from the input side to the output side, where you've got omega S wires crossing. And so you want to evaluate this thing efficiently. The naive thing to do is just sort of put it in, say, topological order and evaluate it gate by gate. And sort of just, okay, these two are touching the input, so this one, if these are both ones, this is a one, and so on. But, you know, if you've got all these different cuts, you might think, well, in order to get from the output, you know, the inputs, I have to keep around like all the values to cross these wires. That's a naive thing, okay, I expect. But it was already known in the 70s, Hopcroft, Paul, Valiant, in 75. Actually, there's an even earlier work cited by Hopcroft, Paul, and Valiant, but it appeared in a journal later, Patterson and Valiant in 76, which showed that this circuit value problem can actually be solved in order S over log S space. You can get this from the Patterson Valiant and say the usual space-bounded simulation of low-depth circuits. And now you can get order S over log S space, but this will need exponential time. It doesn't have to be exponential in the space. It's a little bit less than that, but it's still exponential in like S to some fraction or something like that. So there is like a time-space trade-off to get that sort of thing. You can even get S over log S space and polynomial in S time. So there are time-space trade-offs known. But these things use a sort of pebbling approach, okay, which I will explain more later. And it was known that those sort of approaches require omega S over log S space. Okay, so it was known for a long time that there is some way to do this by sort of recomputing. It's like sort of just save things that you need and aggressively delete, say the values of nodes or gates that you don't need and recompute them. So let's allow yourself some exponential time. And you can save a log S factor doing that. But yeah, as far as I know, people believe that that is more or less the best you could do. Like S, get an S over log S, but not much better.
Maybe it's good to say about pebbling without explaining it, is that it treats the values on the wires of the circuit as atomic.
Sure.
Atomic, values. You don't play with them. You just.
Yeah. I'll say more about pebbling later, but yeah. I mean, there is an approach, and the approach that was used in a whole line of work. So I guess in the dots, there are papers that extend this to other computational models, right? I haven't mentioned the computational model yet. So random access machines and pointer machines and things like that. So this sort of thing is robust. More generally, we like to ask whether everything computable in time t could be simulated in space a little over t, right? And so this is just one canonical problem that takes about linear time to solve. But more generally, you can ask about all of time t, and can you put it in space? How small space can you put it in? And people knew space t over log t. Okay. Also from the same line of work. Now is a good time to mention the model of computation. Maybe I'll draw it over here, staring. I mean, that's important for this work. I've tried my best to make it as unimportant as possible because we would like results that are model independent. We would like results that don't depend on the model. So I have results in the paper that generalize to like slightly more interesting models than this. But the model I'm going to talk about here is the multitape Turing machine. Okay. Also, I'll just call it MTM here. So you have a Turing machine that's got some constant number of tapes. We'll say K. The input comes in on tape 1, some input X. The rest is filled with blanks. These all have blanks. And yeah, like it's the sort of usual action as you would see with a multi-tape with a normal Turing machine, except each head can read, and write and then move left to right independently of the others. Okay, so your transition function is a function of like k different values, and it changes state, and it has k different head movements, left, right, and all that. Okay, so read, write. K cells instead. So this is an old model. I guess it was first used in like the first papers on complexity by Hartmanis and Stearns in the 60s. It is very robust, though. I want to say, for example, it is an open problem to find a problem solvable in linear time on a random access machine. It cannot be solved by this device. Okay. So as far as we know, it's very robust. And we know, for example, up to say polylog factors in the running time is like, as far as we know, multi-tape Turing machine is just as powerful as a random access machine. So we know that this circuit value problem, for example, is in polylog in time. And polylogs, like, I think it's like 2 or 3, the exponent. And sorting and FFT, matrix malls, like all those things. We have algorithms. The way people typically write papers about these is they use, say, a word RAM or something like that. If you allow me a polylog factor, I can get this on the multi-tape machine.
Yes. Sorry, Brian, there's not even anything conjecturally faster in a RAM model? No?
I mean, you could. I mean, I think there are like some sort of target problems, but yeah, I mean, yeah, like the ones you would suspect is like these sorts of things, but actually they don't. They,
Pointer chasing would be natural.
yeah, I mean, there are sort of like index type problems. I mean, even last year I have a paper with my former, well, my current student Rahul, who will be a postdoc here in the fall, where we take a data structure which was random access and actually make it and actually show that it can be implemented on a multi-tape Turing machine. We use this to get circuits for function inversion where we didn't know circuits. Like so it's sorting an FFT and matrix multi, like the fact that they can be done very efficiently can go a long way. So I mean, up to polylog factors, I actually am not sure of a good candidate. Because as long as you can batch things, as long as you can sort of batch like your lookups in a data structure, for example, you can start sorting like across all the queries in the database. So great. So
But presumably, what
yeah.
would be the strongest separation that can?
So we do know, so it could be quadratic. There could be a quadratic separation, but it couldn't be much worse than that. Because the idea is that like, in the worst case with a random access model, like say I want to simulate a random access model on this guy, like I could just write down the entire contents of the memory in some compact way. And then to simulate one step on the RAM, I will just scan through the whole memory for each step. But that's only like, say, O tilde T memory. So O tilde T steps to take one step there. So it could be at most quadratic, you know, for most reasonable RAM models, like where I can write the entire memory down like in O tilde T space. Yeah. So it could be much worse than that. And then that's actually related to an open problem about like improving this to RAMs. Yeah. So good. Yeah. So the main theorem here is that so time t, so problems that can be solved in the time t of n on multi-tape Turing machines can be simulated in space square root of t log t. Okay. Yeah, to me, this is actually very shocking. Like, I think most people would have conjectured, I mean, I definitely would have conjectured that say time t is not in space t to 0.99, you know, so any constant less than 1. And in fact, Sipser in one of the first papers on de-randomization showed that, you know, I should write this somewhere, that Sipser showed that if conjecture and some expanders, explicit expanders exist, then P equals RP. And so I guess Mike Sachs and others eventually showed the expanders do exist. Does it make sense here? Okay. So they eventually showed the expanders exist, but turns out this conjecture apparently is not true. Thankfully, Avi and Noam came along and found weaker conjectures, which we, you know, as far as we know, work. So essentially, in a nutshell, Nissan Vigorson et al. Show that you just need circuit lower bounds on time. You don't need space lower bounds on time. So here, this would be a space lower bound on time, but if you can say like time t does not have circuits of a smaller size, then you can still get rid of the organization. So okay, this is just to illustrate like how weird this theorem is. Yeah, I think it will take a while for us to get used to it, or at least for me to get used to it. So there's a number of corollaries of this thing. Maybe I'll just write it here. So one immediate corollary, which is very weird by itself, is that the circuit value problem is now in space square root of n polylog n. Okay, so this intuition that you need to save even close to S wires, you know, like of values to go from here to here, is just wrong. That in fact you can somehow save some square root of the number of wires that you would need to save. Like the amount of memory you need is much less than just saving like linear memory. And a similar statement is true for essentially any structured dynamic program that you might think of that has T entries in its table, and using a constant number of entries that you've already computed in the table, you want to get the next entry. Now you can save a square root. No matter how complicated the relationship between the entries of this table is. So that's one corollary. Another corollary, which is interesting for circuit complexity, is if you have a size S circuit, so where S is subquadratic, they have 2 to the O tilde square root of S size branching programs. Okay, so if you've got like a linear size circuit, there is a branching program, which is like a decision tree, except on a directly cyclic graph. Okay, you can get something of size about 2 to the square root of n for a linear size circuit. Okay, and this essentially follows from the fact that circuit value problem, right? We can solve it with multi-tape Turing machines efficiently, and once we've got a space-bounded algorithm, we can convert it to a branching program very easily. Like each node of the branching program is just one configuration in the space-bounded computation. But yeah, if you have questions about things, I can give more details. Okay, so another corollary is a lower bound. Now, this is the lower bound that we all believe would be true. The thing we did not believe is that it would ever be proved this way. So for all, say S, for all space-bound, space-constructible functions, so these are just saying nice functions S, space S is not in, I'll just write T for time, S squared over log squared S. Okay. All right, so for example, there are problems we can write down, explicit problems in linear space that need essentially quadratic time to be solved. And this just follows from diagonalization and the space hierarchy theorem. If it rings a bell, I can give a proof if you like. Would you like?
No.
Okay, you would not like. Okay.
I like, but
Yeah.
it's not the main.
I mean,
part of the job.
it's like 3 lines. It's just like 3 inclusions or something. Yeah. So it just follows directly from like just diagonalization with this, say the space hierarchy theorem. Because I can simulate time so space efficiently, but there are always problems I can solve in space S that I cannot solve in space little o of S. So I just use these tracks together. Okay. Great. So another thing I want to mention is that there is an extension to say D-dimensional Turing machines. Maybe I'll just write over here. So, and this is an important extension for me because there are prior results, like for example, the separation of non-deterministic linear time and deterministic linear time, which rely on the fact that it's a multi-tape Turing machine and it only works with like 1-dimensional tapes. So the fact that you can extend what I'm doing to something like 2-dimensional tapes, where the tapes look like that, or 3-dimensional tapes, where the tapes look like that, is interesting. It suggests that there are more things you can do with this kind of approach, and it doesn't necessarily rely on some specific geometry of tapes. So in particular, so I'll just say time sub D for D-dimensional, what you can compute with D-dimensional multi-tape Turing machines, time T. This is in space P log T as before, but with a 1 minus 1 over D plus 1. So it's so that it's 1/2 for D1. And it gets a little worse, right? 2/3, 3/4 as your dimensions go up. Okay. But I'm not going to talk about how to prove that. It's only
So does this
More like-
suggest that if the tape has a structure of an expander, you won't get any?
Oh, if it's like tree-like
Yeah.
or something struck. Yeah, we still are not sure how to do this. So there's a,
Not sure how to do, so you think you do it? You're supposed to get a lower bound or,
oh, do I?
an upper bound? How should I view it? An upper bound?
Right, so this is an upper bound, yeah. We don't know how to extend it to, say, tree-like tapes. So like where the tape is a tree, like a tree structure. Yeah, we don't know how to do that yet. We can do it if the head movements, like, you know, can be calculated in advance. So like if it's oblivious, we can do it. But it's just like there's like some conditional saying, oh, if you do this, then you go this way or this way. And we don't know how this condition will evaluate to based on the input. We don't know how to do it yet. Yeah, but I don't think that's inherent. I can explain why I don't think it's inherent later. But
Don't think it's-
okay. I think it probably can be extended. Probably we have to break open. Sorry?
You think this is the correct, like 1/d is like, you know, instead of the half,
Yeah.
you think that's correct?
Oh, I think this is correct.
Yeah.
Oh, not necessarily, no. So that's my next point is, can this theorem be improved, right? I actually am not sure what to believe now because I didn't believe t to the 0.99, there's a square root there now. So I actually am not sure what to think. I mean, there are some opportunities to do a recursion. I just am not sure how to do the recursion. But I mean, there is a possibility of like doing some, like calling the thing on itself in a certain way. So, but I just want to point out that like, if we did manage to do some nice recursion and get, you know, space t to the epsilon for all epsilon, then we would definitely have by then p different from PSPACE, also by diagonalization. Okay. I don't actually have a guess about what the correct epsilon is anymore. I would have said it's 1. I mean, basically. So I don't really know. Yeah, and this you know also follows from diagonalization. If you assume this is not true and you assume this, you can get a contradiction. You can show that space S can be simulated in space a little less. Great. Any questions? Are we doing okay? Great. Right, so let me say a little bit about this prior theorem, because they already developed some ways of thinking about time-bounded computation, which we will use. Okay, okay. So we're given here like a multi-tape Turing machine, and we're given an input X. We'll say it's got K tapes. So we're going to do some partitioning on the tapes of our machine. So we'll partition them into some tape blocks. Maybe first, like, set some parameters. I'm going to think here, just for simplicity, that T of n is at least n squared, so that I don't have to think about like small time bounds. I'm gonna say like some block size is square root of t, and I'll do something about square root of t asymptotically, where b divides t. And the idea is I'm gonna partition these tapes up into blocks of B cells each. Okay, so B cells, B cells, B cells. So I'll have these tape blocks that have about square root of t cells in each block. And I'm going to define a computation graph. So talking about how the information computed at different blocks relate to each other. Okay. So I'm going to define a directed acyclic graph, G sub mx. And so each node will represent B steps of time. Okay. And so there'll be about T over B nodes. Okay. And I'll label them 0, 1 through T over B. And like this, so this 0 will just be like, what does the machine look like at the beginning? So this will represent sort of the initial configuration. This will represent what happens after B steps, what happens after 2 B steps, and so on. Okay. So we're thinking of just dividing the computation up into these time blocks. Okay, so we have tape blocks, and we have time blocks of B steps. And the observation that we're going to use here is, so during a time block, at most 2 tape blocks are accessed for each tape. Okay. Right, the idea is that, okay, you know, if I'm running around for B steps and these things are B long, right, I can only intersect at most 2 of them. It's nothing fancy going on here.
Also for B equals 1.
True also for B equals 1.
You can take any B.
You could take any B you like. Yes. Yes, this is independent of the choice of B. You know, most of the things I will say are independent of the choice of B. Yeah, right. Yeah, good point. Yeah, so we're going to have some graph that will tell us what information from the past we need to compute the present node, say the node I. Okay, so for I less than J, because this is a DAG, we want to have order, we put an edge ij. Roughly speaking, if the info that we get at the end of time block I is needed to do J. So for example, I minus 1I is always an edge. Because the idea is that we always need like the state and the head position from the previous time block to start up the next time block. Okay, so here we need state and head positions. Okay, like of all the tapes, all right, which we could get from, so the information computed time block I includes whatever state we ended, whatever head positions we have. But also there's another situation, right? Like if there exists a tape block like visited and time block I and time block J, that both I and J, let's write like this I and J, but not visited, not accessed, and anything in between. All right. Then we would put an edge, right? So like if you visit some particular tape block and you go away, you come back in J, you haven't touched it since, you need it. You need this information. Right. So that's the other situation which we would put an edge. Okay.
Say that again, sorry.
Yeah.
The
So
other situation?
yeah. So for one, we need the state and head position from the immediate time block. Let's say that's computed. But also, like imagine so like in time, I'll try to draw a picture. So let's say in time block I'm reading this one here. I go away, and then I come back to it in time block J. Then I need the content of this. That's all, right? Because I went away and I came back. So it's not visited in I plus 1 through J minus 1. That's all. It's just sort of exactly the information that you need. Yeah. So it's just it's really just this intuition.
When you say time block I, you mean the blocks that were read in time I.
No, I mean that I'm dividing time into blocks of B steps.
Divided the tapes and the time.
Yes,
So after several steps, then okay, after
yeah.
steps of length B, okay, so what is block I? What do you mean?
Sorry?
So what do you mean by time block I? Say it again.
So I mean, like the time, the B steps you take
Yeah.
after taking, I guess I minus one, or basically I times B plus one, like time, like that, like what you're doing at that time.
Yeah, but what blocks? So after I times, and I understand the time, but then like
There's
what blocks
blocks on the tape, but there's also blocks of time.
Call them like hours or
Yeah,
minutes. or something.
it's meta steps and meta memory units, that's,
Yeah.
just,
Okay.
but you only need, if you're going to access some cell or block, you only need to know what it was in the last time it was changed. It was possible to change, this is all it says.
Yeah, so the idea is, let's say this thing is running, right, from time 0 to time t. I'm dividing that thing up into B steps as well. Okay, like this is like, and this could be like the configuration of the machine at every point in time. But there's only, for B steps, I don't need the entire configuration of the machine because I'm only processing for B steps. I only need like some local information, like all the information I could possibly access in B steps. And that's what these edges are sort of telling me. What information do I need? Yeah. Good, so the degree of each of these nodes is, well, we access at most 2 tape blocks for each tape, and we need an edge for these state in that position, so the degree of each node is at most 2k plus 1, right? For each tape, I access at most 2 different tape blocks, which could have been touched in different time blocks in the past. And then I need 1 more for this edge from I minus 1 to I. Okay, the point is that this degree is constant. That's the point. So this is the end degree.
Just to be clear on this, I'm sorry.
Yeah.
So every tape can cross 2 tape blocks.
Yeah,
And if I cross some tape block J, it means I need to have an edge to some earlier time block, not necessarily J. Basically, the last guy who used that.
the last guy that accessed it. Yeah, that's all. Right, but the point is that in B steps, there's only so much information I could have touched.
Right.
And like, if I think about the tape blocks, then there's only at most like 2k plus 1 tape blocks that matter.
Right.
Yeah, basically, yeah.
This thing would work if B was 1, it would be just a computation graph of
Yeah,
the Turing machine. You just make the Turing machine more powerful. It can do what it used to do in B steps, it does in 1.
yeah. Yeah.
Nobody so clear you did that.
In
Strong.
In fact, the generalization to RAMs, needs the B equals 1, because we don't actually know how to draw this graph, and they don't draw that graph. They do some implicit thing, and the graph arises in analysis. So like you can set B equals 1, you can set B equals square root T, whatever works. For us, square root T is nice, but yeah. Good. Right, so the end degree is constant, that's important. And so now we want to sort of define like strings, which will represent the content we computed at each time block. Okay, so we will say like the content of node 0. So our node 0 is just the initial configuration. Okay, of n on x, and that takes order n bits to write down. Okay, I have set t of n to be at least n squared, so I don't have to worry about that. In general, if t were smaller, then I would need to have contents. I would need to have my initial content broken up into separate blocks, like I would have like blocks that break up the input here. It makes it a little more complicated, but doesn't mean it can be done. This is just,
The initial configuration is T block, N is the size of the input, so
yeah, right. And that's, sorry, I always, this is, yeah. It is the size of the input, right? And I set the block size so that it's fine, okay. So that it fits in the block. And then, right, content, I is just, whatever info computed. Like, just all the tape blocks you access there, and the state and head position at the end of the block. So the state and head position at the end, the contents of the tape box.
Probably T.
Yeah, so this will take order B bits. Yes, perfect key. Yep.
So do you also include everything that you don't compute, but that is in the blocks that you access?
Yeah, I'm just going ahead and include the whole tape block.
Yeah.
Yeah, so if I access it, but maybe I don't write, I'll just go ahead and include it. Yeah, just for convenience. Yeah, and so the observation here is that, if you're given this content I, and it's for all I such that ij is an edge, then you can just compute. You can get content j. And you can do this in order b time. Is this too low? Is it visible? No, it's fine. Okay. Right. So if in other words, like if I'm in this DAG and I've got like all the predecessors of some node, if I've got their content, I can compute the node's content. And I can do it by just literally simulating the Turing machine. Okay, in order B steps, because I've got all the information I need, got all the head positions, the state and all that. I can do it. Okay. So now our goal is to determine the content of the last node, right? Content T over B. Okay. Right. So the way that this has been done in the past is through something called a pebble game. And it's a game played on a DAG like ours. Let's say it's an node DAG. And there are some rules. You can't put pebble on the source, any source, like our initial configuration. You can always compute source. So if you're given pebbles on all I such that ij is an edge, you can pebble j. Okay. And pebble j. And you can remove any pebbles anytime. You can remove any pebbles you want, okay, at any point in time. Okay. So the idea here is to model the memory usage of a potential algorithm that's trying to, say, evaluate a circuit, compute this DAG, compute the last node on this DAG by saying, okay, if I've got the contents of the predecessors, I can compute a node, but I want to be very aggressive about memory usage. I'm going to just erase if I don't need something until much later, say. And then if I need something later, I'll just recompute it. Okay. So this, it's a simple little one-player game, and the question is, how many pebbles to get, say, any node, to pebble any node. I'm going to say last node, whatever, in your topological order. You get a pebble on it. And the answer is order n log n for graphs that have, so with order 1 n degree, it gets worse. I think the n degree is actually in there, in the numerator there. And this is tight. So there are like examples where you actually need an over log n such pebbles. So as far as we know, this is the best we can do, right? So that's how prior work worked. And the idea is that this pebble game strategy, it can be sort of computed in low space. There is a way to do this in a low space efficient way. And so if you do this in over log n thing, right, for us, this corresponds to so we like store order T over B divided by log T over B nodes at any time. These are all content strings of order B length. Right, so that will give us setting B to be square root of T. This will give us our T over log T space. Okay, so we're storing this times this space at any point in time. Because each pebble, right, takes order B bits for us to write down. Is it all right? Yeah, okay, so let's see how to go towards low space. All right, I have run on the board at just the time. Let's see. So the starting point of getting a smaller space algorithm using a similar idea is this so-called tree evaluation algorithm. So this tree evaluation problem. Yeah, I hope this is clear. Like I've actually tried to write it in such an abstract way that you could imagine how it might be applicable to things beyond multi-tape Turing machines. It's just about like getting the information you want at the time you need it. So I hope we like made it. Okay. So yeah, so this was first studied by Braverman, Cook, McKenzie, Santanam, and in 2009 as a candidate problem for separating log space from P. So we have these parameters. Actually, can people see over there from here? Oh, I can just erase this one right here.
What's the most of it? Just move like 3 inches to the right.
3 inches. Oh yeah, I can already see this. Okay, because I want to draw a tree and all that stuff, and I want you to see what you did. Yeah, okay. Yeah. So B and H are parameters for us. Okay, we have a D-ary tree of height H. Okay. So we've got D to the H minus 1 over D minus 1 nodes. Okay. Right, so we're gonna think of this as so tree, the area, each inner node, so I'll say each inner node, call it U, has a function F sub U, which takes dB bits and outputs B bits. Okay. And the leaves are labeled with a B bit string. Okay. So we think of the leaf L as having some value A sub L. Okay. We've got some leaves down here. They've got B bit strings on them. There's a function being computed in each node. And we define the value of an inner node in a natural way. Given the values of the children, we apply the function f to get the value of the current node. Okay. Right. So you can think of this as just some kind of formula evaluation on something of formula of depth about H, and the formula takes in D inputs. Each input is a B bit string, and we're just evaluating it, okay? Starting from having full values of the leaves. All right. So then our task is to just compute value of root. Okay. Value of root.
The input size is about b times d to the h.
The input size is, so we store an entire table for each of these. So for each of these nodes, right, we have 2 to the dB times b bits. So the input size is this times this. Right, so we think of, so if d is a fixed constant, then it's like 2 to the order b plus h. Because
To be petty.
Yes, yes.
To understand, you go from the leaves to the, so
Yes.
the tree technically has d plus one. Every node has d plus one edges out of it, like d from below and one heading up.
oh yeah, it's a d-ary tree. Yeah. So it's got d here and it's got one, yeah.
Okay, okay.
It's got, yeah, as a graph, it has,
It's not like.
It has
you
degree
got-
d
you
plus
got
one.
All the.
as a graph, it has d plus one.
Okay,
Yes.
Roosted.
Yeah. Right. Right, so it's, yeah, so the input length is theta. H plus b at the, yeah. Right. For constant d. And the question is sort of how much space does it take to compute the value of the root? Maybe I'll write over. I don't need pebbles anymore. And so how much space does it take? Well, one easy thing to see is that you can do d times h times b space. Okay, by just a simple depth first search. But the idea is that at every level, right, you only need to store about d of the b-bit strings that you're holding it in memory. And so just a sort of depth first search, you go down here, you compute this one here, you have to store the value here before you get the next one, right? Like, so like if you're somewhere in the middle, you need to store like the d minus one values here, it seems like while you're recursively computing this one. So you need, to store d minus one values, d minus one values, d minus one values in the worst case. And these are all b-bit strings and the height is h. So you get the product of all 3 things. That makes sense as a simple depth first search sort of. You're aggressively reusing space as much as you can, but it takes as much. And if you try to sort of use a pebbling argument, this is what you will get. Right, so Braverman et al., they show lower bounds and restricted settings for this, and they conjecture that this HEP is not an NL. That is still open, whether it is an L or not. But Cook and Mertz showed last year that actually this problem can be solved in surprisingly lower space. So we solve in h times log dB plus d times b space. Okay, so
Roughly h plus b other than h.
yeah. So it's like O tilde h plus b, or something with some low order term in the front of h. It's very close to h plus b. And so in fact, like in terms of the input length n, this is something like space log n times log n, which one can improve. I guess Oded has a papers as log n times log divided by log. That is not useful for us. We actually need the parameters. Like we actually want this bound for our bound. Turns out. Yeah, I mean, I don't know if I have. Well, apparently, I only have like 10 minutes, so I definitely don't have time to describe how this algorithm works, but I could give some intuition later. Yes.
As we said, you can definitely take your time and don't worry.
Oh, okay.
But Ian Miles gave a talk about this last year. It's on the video archived. He gave a great talk.
Yeah. So Ian has given a great talk about this. The intuition, I guess, that I have about it is that, okay, in the depth first algorithm, every time you're writing like one of these values to store for later, you're writing it in fresh memory, like every time. You have erased what you had before and you're writing it in fresh memory. Well, I mean, it turns out you don't have to write it in fresh memory. You can just XOR the value you have into a register which is already sitting there. So in fact, like what there will be is there will be about D registers of B bits that you aggressively reuse, like over and over and over at every level of recursion. You will still store a little bit of info in a depth first manner as you go down the tree, but you don't store an entire B-bit record. You store log of that, roughly, like a little pointer, like saying where you are. And so what you end up doing is you get some recursive algorithm which says, okay, I will show you how to add the value of my current node into any register you want, assuming you have an oracle for adding the value into for each of the children. So assuming you have an oracle for adding the value of a child into any register you want, I will show you how to add the value of the current node into any register you want. And the way you can do this value is by polynomial interpolation. So you actually don't care what the current content of the register is. You will just say, tell me what the register is. I will multiply that register by some appropriate root of unity to some power and add it with the value of the child, okay, which I know I can get. So I can think of each of these functions being evaluated in a natural way to say a low degree extension, a multilinear extension. And instead of sort of trying to evaluate the thing directly, I just compute the multilinear extension over these particular values. So like someone adversarially tells me the register is X. I can't control that because that's coming from like my depth first recursion. So what I will do is I will multiply by appropriate root of unity to the I plus the value of my child. Okay, and I will do this for I have D registers, so I'll do it for the different D children I have. So like D1 and neg I X plus VD, okay? And once I've got this, I'll just evaluate my polynomial at this, okay? I'll just evaluate my polynomial at these points. Okay, which is the function. I'll evaluate the function, let's say we think of it as a polynomial at these points. Okay, but then I'll just use the fact that if I chose my root of unity nicely, I could sum over something which is like, let's say O tilde dB, or let's say poly dB. All these things will cancel and actually give me the value of my polynomial at the children. But if this is actually computing the function, this just gives me the value of the function. So this gives me the value of my current node. All right. So given the values of the children, I can get the value of the current node by some polynomial interpolation trick. You see, like I don't have to, like X could be anything, could be any memory whatsoever. And I will just have some algorithm which will recursively add in the value of the child into any register I want, and I will get it to add the value of the current node into any register I want. And so this is a super high level idea. So instead of allocating new memory, I just XOR in, but I do it in a very, very careful way to cancel out the bad memory I have and get the value I want at the end. All right, I hope that's enough intuition for now. Okay. Sorry if that didn't make any sense.
Anyway, you're going to use this result in black box.
I use this as a complete black box. Yes. I go to links to not break open the black box. Yeah.
But it's also clear how non-pebble like this is.
Yes, it's very it's like XORing the value of a pebble with another pebble. And then like doing some weird sum over pebbles like times the value from a field to a pebble value. Yeah, there's a lot of, yeah, it's very non-heavy. Well, that's exactly what like the starting point of here is that this is only writing content into blank space, which is what the pebble game models. So this is model some, so to model this, you would need some game that XORs the values of pebbles into other things that can multiply those values by other things. And yeah, okay, but okay, I'll just erase all that stuff except for the bottom. Right, so how are we going to prove the theorem? So this guy here. So again, we're given an m and an x. We're just going to reduce to an exponential size tree evaluation instance, which we will access implicitly. Okay, we will never store the entire exponential thing. We will always just access it in some implicit fashion and use the fact, like just using small space, and we'll use the fact that we have a nice tree evaluation algorithm. So let's say this thing is time t. Now we'll just start by assume that we know the computation graph. Okay, assume we know it. Right? And there's we have to do work to make this assumption, but so like either it's stored in memory or we can compute given I and j whether there's an edge like efficiently, something like that. Okay, so somehow we know it. All right, so we set b so that for all I, content of I, the length of that is at most b. All right, so actually this b will be a bit larger than the b we had up there because then it's like an order b. Okay, so we'll set our b to be a constant factor larger we had last time, and we'll set d to be 2k plus 1, and we'll set h to be t over b plus 1. So these are the parameters for the tree evaluation problem. Okay. And so right, like the degree is at most 2k plus 1, and the content is at most b, and maybe the height is not exactly always t over b, depending on how we look at it. But we can extend Cook-Mertz so that we're not looking at a complete d-ary tree, but like every fan is at most d, its maximum height is at most h, and so on. Like the algorithm works with major modification. The main thing is that we use the fact, sort of build on the fact that Boolean circuits of depth h can be simulated by Boolean formulas of depth h. So this is true for Boolean formulas, and it is true for formulas that take in b-bit values and output a b-bit string. So I have a little example of it. I could just say right now, it works for b-bit circuits in b-bit formulas. The point is that if I have a b-bit formula of depth h, and its fan-in is at most d, this is literally tree evaluation. That's the main point. So if I have a formula that manipulates b-bit values at every node, okay, has fan-in at most d and depth at most h, this is just equivalent to tree evaluation. Okay. Right. The way this is done is sort of just unrolling from the thing, starting from like the source node. So just unrolling it backwards. So like for all the different paths that you might take from the single sink to a source, you will have like a path in your formula.
How did we move from circuits to formula?
You just open the multiple out.
Oh, I can draw a little picture if it helps. Okay. I have to see, I have a nice little picture. I brought my colored chalk for it too. If you really want. But okay, yeah, okay, so the point is that, right, I can think of what I want to compute on this graph as a B-bit circuit. It's got H total gates, so its height or its depth unrolled is a formula is certainly no more than that. Okay, so then if I just use, okay, I can erase this thing here. If I just use Cook and Mertz directly on this thing, so the Cook and Mertz space, right, will tell me that this is, so theta B, because D is a constant for us, K is the number of tapes, plus theta T over B, log B, and then we set B to minimize. And that's exactly how we get square root T over P. Okay, we just set B to minimize these two. Right, okay, but we don't know the graph. All right, that's the problem. I mean, if we, like, this sort of graph makes sense for literally any interesting model of computation. So if whenever we know the graph, we can do this, okay? So actually knowing the graph is important for the result.
In small space.
In small space, yeah, you can, yeah, because space is extremely robust. Like space on a RAM is basically the same as space on a multi-tape Turing machine, up to polylogs, and we don't even care about polylogs now. We're square rooting things. So yeah. I mean, the whole game is to sort of know the graph somehow, like get our hands on the graph. So the easiest fix to get our hands on the graph is to make the Turing machine structure without blowing up the time by too much. Okay, so say M is oblivious. Okay, if for all n, for all x length n, the head movements, head moves of M depend only on n. Okay. So this can be done. So there's a theorem starting with the simulation of Henny and Stearns from 66, and also Hibbeter and Fisher from 79, that says you can do this. So we can make oblivious with the time blowing up to order T log T. And in fact, we can make the machine have only 2 tapes, even if it has some arbitrary constant number of tapes to begin with. But moreover, given n and given any I can, so let's say n is written in binary, and given any I, where I ranges from 1 to T, so we're in an order log T bits, I can determine exactly what the head positions are in polylog T time. So this is so structured that I can just compute in advance where all the head movements are going to be. Okay. All right.
So this is just for Turing machine.
This is just for multi-tape Turing machines. Yes. Yes. But the point is, once you can do that, once you can calculate in advance where all the head positions are, the game is over. Like that's all you ever wanted to compute in the edges, right? You just look at what tape blocks are visited and not visited and when, so you're done. Okay, so you can just write down this computation graph in your memory. Okay, like if you just do it in the most naive way, that'll take number of blocks of T over B times log B space. We were already paying that, I guess. So we're already paying something like that because T over B is the same as B, square root. So I could just write down the graph, like after computing for every single IJ, like whether it's an edge, if I want, like, you know, it's based on a computation, I don't care about the time. So once I've computed this entire graph, I can run the argument and so now I can just reduce immediately the tree evaluation. Okay, but of course, I blew it up by tlogt here, right? So that doesn't give me this square root, and this thing will give me instead order square root t log t.
We don't care.
We don't care, yeah. We don't care that much, yeah. I mean, well, I care because I would like to be the case that with tree evaluations in log space, then I get a clean square root. So that's the only reason I care. But I do spend more pages, way more pages to make us to care about it. Yeah, yeah. Right. But yeah, but it's like because it seems pretty natural that tree evaluation maybe is in log space, and so if it is, then we also remove like these other factors. Okay.
Can you
So-
say something about the oblivious? How do you do that?
Yeah.
To solve, basically.
Oh, sure. Yeah, you could think of it as a sorting network. Yeah, you could think of it as running a sorting network on the, like where the reads and writes will be. Yeah, I mean, there is an explicit schedule you can write down. Like imagine that it's infinite in both directions for simplicity. Then the idea is you would simulate it this way for one step, this way for one step. Then this way for one step, this way for one step, this way for two steps, this way for two steps. Then do the whole thing again, but with that power of another power of two steps. The whole thing again, with another power of two steps. So that's an explicit schedule you can set on the head movements. And so you can, it's just a little arithmetic to figure out, okay, at step I, where am I going to be? Do you agree, Eric? I can't, okay. You're particularly interested in this point, so okay, all right. Yeah. So right, it's just like, it's a simple sequence, so you could just compute, given I, like where you're going, like what the head position is going to be. Yeah. Let's not talk about what it does, but that's the movement, right? That's the movement. Yeah. Good. Do you really not care? Because I mean, we can end the talk now. I go to open problems. Oh, he reads the boss. Oh. I don't understand. Okay.
Yeah, the speaker should speak about what.
Okay, yeah, I mean, I can just say like really quickly how you get rid of the thing. Considering we're near the end, I can just use this, I guess. So, right, so to get the full thing so that if you manage to get log space, the tree evaluation, you get exactly square root. You don't make it oblivious. You guess the graph. You have to be clever about how you guess the graph. And you check that the graph is valid. Okay, both of these are a little non-trivial. So in order to guess a graph and not use too much space, so I mean, it turns out that like we can only use, we get away with order t over b bits. Okay. And the idea is that we like from one time block to another time block, the tape block that we access can only change by like 0, 1, or -1, right? And the ones that we might access is like a subset of those three, like changes in index. So like from one time block to another, right? There's only at most two things we could access. So if I know the current tape blocks, then the tape blocks at the end of the current time block will only have incremented or decremented or stayed the same, right? Like and the ones that accessed would only be some, +1 or -1 of the index of the previous ones. Okay, so this just involves like storing constant number of bits for every node in the graph. Okay, so we're just going to try all of them. Okay, try all such encodings of them. All right. Now, okay, so let's say we've got a G prime. We're trying to check that it's actually a good graph. Okay, well, we've got these functions, right? So this G prime like asserts exactly, which blocks are accessed, which state blocks are accessed, and when. So I want to check that it doesn't make some violation. So what I'm going to do is I'll put this in my tree evaluation problem functions. So my tree evaluation function for say some node I will depend on G prime and node I. Okay, and the idea is when I'm simulating M in time block I, if some head violates the assertion, like says, "Oh, I'm accessing something I wasn't supposed to access," then so if in a violation, I just have like VI output fail, just output some fail string. Okay, and I check at the beginning if any of my inputs is a fail string, I output fail. Okay, so if there's any like weirdness going on in the head movement that doesn't obey the assertions of this graph, then I'll just fail, and the fail will propagate up all the way to the root. And so my instance doesn't output fail, doesn't fail if and only if I've actually got my hands on the right graph. Okay. Right, so that's how I make it a black box thing to tree evaluation. Yeah, so that's in a nutshell. I guess I can. So yeah, I mean, from this it's pretty easy to work out that if tree evaluation is actually in log space, then you will get exactly square root of t. Right. Because that would mean you get space h plus b, both of which are square root. Like we can set the square root.
So your best is that it really is in log space, or you're not making that bet?
I don't know what to bet exactly anymore, but I thought like it's a natural thing to try to prove. yeah, it's some natural thing to try to go for. So yeah. I mean, I thought that there should be a way to combine Hopcroft pebbling arguments and this stuff to just eliminate the log without settling the complexity of tree evaluation. But I haven't been able to do that exactly. Yeah. But I think it's totally possible you might get the square root of t without like, yeah, figuring out what how the space efficient tree evaluation is. So let me just conclude with some problems. So the first one is to extend to RAMs, extend to random access models. That's a very natural thing to try. So in particular, like we'd like to know, let's say time on a RAM, t is in space, t to the 1 minus epsilon. Okay. Another one is to extend to alternating time. So alternating time is this generalization of non-deterministic and co-non-determinism, where you can enter non-deterministic, co-non-deterministic in any particular step. I mean, it effectively models like quantified Boolean formulas. So if I were able to show instead of a space upper bound and alternating time upper bound, I would have a lower bound on solving quantified Boolean formulas. So right now I just have a lower bound on solving linear space problems. And yeah, so this is asking whether the time t is an alternating time e to the 1 minus epsilon. And an interesting question, seems weaker than these two things, is whether you can just improve what I have already. You can get half minus epsilon. But it's not hard to show that it actually, if you resolve bullet 3, you get bullets 1 and 2. Okay, because if I manage to get less than a square root space here, right, I can put time on a RAM t in multitape time t squared, right? So if I manage to get less than square root and I have got a better space efficient simulation on RAMs. Okay, and similarly, like if like I can put space s in alternating time s squared. So if I got this, then I can get this by just squaring the exponent. Okay, so actually, bullet 3 is more would resolve both of these. And of course, like, you know, whether you can get something even better, like 2 to the epsilon for all epsilon is nice. Of course, you can always ask whether there's a barrier, but I find myself very lucky that I found this reduction after Cook-Mertz, because I would have definitely declared this to be a barrier. Otherwise, I would have said, if tree evaluation is in less than log squared over log space, we improve Hopcroft polyvariant, which we're not going to do. So don't think about this problem. You know, so luckily I didn't see this. Luckily I didn't think about this until. Yeah, I mean, this is like a philosophical point for complexity theorists to ponder. How many barriers do we actually have? Like maybe we should be thinking more about algorithms instead of intimidating each other into not thinking about algorithms. Yeah.
So have you tried to do counting hierarchy instead of space? It's more than alternating, but less than space.
Oh, counting hierarchy. So right, like exponential TC0 type stuff. Yeah, that's an interesting thought. But you still mean like finite. So this would be like exponential NC1. So
Oh, I see.
constant, like exponential TC0 would actually be even stronger than this, but maybe you could have like some small unbounded.
No, I think
But
like, there's a version of alternating machines where it's like thresholds.
yeah.
So it would be the same thing for counting time.
Yeah, but is that actually is that actually like a stronger statement than getting the space though? Because like,
It should be easier to, I mean, they can simulate alternating machines, so.
yeah. I just mean that like, if I got this generalization of alternating time and like, would that actually be better than having the space bound? Would actually be better than having a good space bound? Like I thought you would need to store some intermediate values, maybe not. We're using tree evaluation. But would I need to store some intermediate values to do this alternating counting thing? Yeah, I feel like having the space bound is actually a tighter bound than that, maybe. But I'm not sure. Yeah. Okay.
Okay, let's thank Ryan.